Hello, I just wanted to go over the Libre-SOC IEEE754 multiplier, floating point multiplier, to show how everything fits together. So here we have three major blocks. The idea is that this is capturing the input, and it contains ready and valid signaling, just like in Wishbone Axie4. It's based on Dan Gisselquist's pipeline synchronization, and also on the Chisel IO library. So then that feeds into the actual ALU. Now this can be it's multi-in and multi-out. Okay, so this is why you have so it's multi-in, single out, because this is a multi-stage pipeline block, and to keep it fed, you have to, in a 6600 design, you have to have concurrent function units, which Mitch also very kindly explained. And the way that works is any data that you need for the ALU. So if you have a 4-stage pipeline, you need a minimum of 4 what they call function units at the front of it to capture the data and feed them on contiguous cycles. But you need an identifier to go with that, so that when it comes to the so that's the input. There you go, that's the MUX ID. Sorry, I was looking at the wrong one. There's your MUX ID, and that is used on a to fan out back on the output. So you have 4 possible inputs here, 4 possible inputs on the incoming parameters. That's why you have MUX ID, 1, 2, 3, 4 there. Let's have a look inside that. Show in pipe. Okay, so there's your MUX selector, the parallel MUX, which selects between the. But what that does is it only allows one of the inputs to be selected. But there's also a mask for cancelling them included here as well. So that's so this is, we need this as a single block. Now this is a where is it? Yeah, here we have the latches for A, B, and C. So it's a synchronous block, passing its data crossing with a ready and valid signaling. But we need only one of those to go through at one time. So that's your input selector between 4 in, 1 out at a time, going to the ALU, and then it goes back to the output, so that you can fan out, so that it can store those results in the output. And they can be selected, ready to go into the register file afterwards without losing the data. Show the ALU itself. This is divided down into again 3 different blocks, each of which has again pipeline registers in between them. So your A, B and C go into this first block. C is because it's a floating point multiply and add. C we're currently not using at the moment. That's for later. So you have a series of special cases and normalization. Special cases is things like multiply infinity by infinity, multiply A by 0, multiply B by etc. etc. All of those are I'm talking. Thanks, Paul. Those are sludge. Those are handled separately here, and there's a couple of ways to do it. One is that we could have a pipeline early out bypass, or we could just pass it through the stages and say, look, don't touch this data, don't do anything. So let's have a look into SC norm. Show SC norm, special cases and normalization. Okay, so these are all combinatorial blocks. Okay, the combinatorial blocks here, so here's your special cases, here's the denormalize phase, and here's the alignment phase. But there's the storing, there's the latches for this particular phase on the output, with the ready output, valid and ready thing. So it's all chain with those latches. So if for special cases, let's have a look in special cases. Here you have the detection. This is a special case decode for A and B, which says it's if an infinite or not a number or 0, and likewise for B. And then based on that, it will make a decision of whether the result is infinite, whether it's 0, etc., etc., whether it's not a number, and so on. And will give either a result and an indication that it is special here, it's a special type, and to give you the result. Now that will be so SC norm, SC special cases. So if it's not special, then that out do Z, which is about a bypass thing, goes through and tells all of the other phages, hey guys, we've got the result ready already. Don't do anything. Don't try any denormalization. Don't try any packing, alignment. Don't do anything because the result's already. We could do a pipeline bypass from here, which we're giving serious consideration to doing that because it saves time. You've already got the answer there. Why would you pass it through? So denormalize to denormalize. Denormalize is basically have you got the exponent, is it negative -127, and if so, you need to shift, you need to adjust the exponent, adding in a 1 at the end. Is do it IEEE. So it's this stage is actually quite simple, which is why it's a combinatorial block. Where are we? SC decode. No, we didn't want that. SC norm. Special cases. Let's go back to ALU. Yeah, that was the SC norm block. Okay, alright, so we've done that one. So here we know, by this point we know that the mantissas are all lined up they've been shifted up. So we're ready now to do the multiplication. So mul stages. Here you get, again, it's relatively simple. It's divided down to mul 0 and mul 1. Again, these are currently common order auto box, but we actually don't want them to be. Explain that in a minute. Mul 0 stage is very, very simple on paper. This here is a 64-bit 64-bit multiply A by B, 64-bit and 60 the thing. Hence the 107-bit, because multiplying both the mantisses together. Hence the 107-bit output. That's completely not possible. So this block here is going to have to replace by a multi-stage pipeline involving a data multiplier, and because it's going to be I think we may use it as a partition. You would use the integer partitioned pipeline and just say, please do us that will be a 64-bit in, 64-bit 128-bit output, but we'll just use 107 bits of it only. So there's another set of stages in here, but this is massive. This single block here, if we left it on its own, for the for yosys to create a block, it would be absolutely massive. So don't be fooled by that one single looking block. So once that's so multiply 1, again relatively simple. This is just really show you the code here, but never mind. This is this bit here is the sticky bit on the remainder, because it's calculating the guard and the rounding as where the rounding is needed, etc., etc. Plus it's also adding 1 on the exponent, and yeah, it's adding 1 to the exponent and working out. Yeah, this is easier if we look at the source code. But oh yeah, there's a shift. Here we go. We're shifting the product, so we're doing a small amount of normalization on the on the product. So if the last bit, yes, if MSB is, that's right. If the MSB of the mantissa is a 0, you need to shift it, and yeah, you get the idea. Shift it along so that and add 1 to the exponent. Sorry, subtract 1 for the exponent. Yeah, that's it. You multiply by the mantissa by 2 and subtract 1 from the exponent if and that's what the shift is for multiply by 2, if the top bit of the MSB is 0, which it may well be. Then that was calculating the round, for rounding for thing. All right. So those are your multiply stages. All right. So back to ALU, back up a level to ALU, and finally we have a normalization packing. So norm and pack. Norm pack. Again, a chain, 4 combinatorial blocks. Normalize, rounding, some corrections, done, and finally packing the result. And that pack is very, very simple, and could be actually a dummy or just a blank thing. If we look at normalize, here in a single stage, it's actually, if we have to do a multi-bit shifter. So we're working out if here we're working out whether the normalization needs to take place, and then if we look in norm exp, normalize on the exponent, in the previous stage you worked out how many bits the MSB. So the thing with the floating point number is the output. The mantissa has to have an implicit 1, so it's going to be 1.0011 however, to get that implicit 1, we've just calculated a product where there may be several bits of the zero, so the MSB is not 1, and consequently you need to shift up, but we need to do it in a single cycle. So in the previous stage you work out how much shifting is needed, EDIF, and then perform a multi-level shift, a single stage multi-shift R, but we need to put in a mask because you need to shift a 1 into. It's complicated. So the reason this thing. So this is the thank you, doggy. Shush, Lizzie, shush. So stay up my mum's. Let's come back. It's a complicated design that we could only sensibly do as hierarchical classes. Therefore, you have all of these blocks, which will need to be laid out. Thing, but it's basically the data it's always forward facing. It doesn't wrap back around on itself, except right back at the top level. But not even in this at this point. It doesn't wrap back around. This is with the in pipe and the ALU and the out pipe. It's the user of this ALU that has the wraparound data, because that's where the register, the dependency matrices tell say whether it is safe to read from the and the data is valid in the register file to put into the input latches here on in pipe. Then it goes through the ALU, and a few cycles later it will be ready in the out pipe, and you will have the ready and the valid output, indicating when those valid O signals are ready. That says to the picker, the priority picker that manages the right register file data bus, that the data is ready to be written into, can be selected depending on availability for writing into the register file, or we will actually have register file bypass detection, and it may actually go, the data may go from here directly into another function unit in pipe, into one of these AB, I think A0, A1, A2 or A3 thing. So I apologise for the I apologise for the and erring and for the interruptions. That gives you an overview of just one of the ALUs, and we need a minimum of 4 of these floating point multipliers next to floating point div units, etc., etc. Thank you very much.